So I got 1.5 hours. So I'll be talking about the word embedding and what to make, and the modern language processing technique, how it could be useful. So I'll be going over this, and stop me anytime if you have any question, any concern, you want to discuss something. If it's a longer question, maybe you can stop for some while. But it's a immediate question, clarification, etc. You can stop anytime. Okay. So let us get started. And if you have if you know it, most of the people and etc., you can also say that we know it, and you can jump or you can skip and etc., all those things. So before starting, let me understand my audience little bit. So most of the people here are bachelor students or master students, or you know how many faculty members?
So, Amitabh, all are faculty members.
Okay.
Very few PG students are there.
Okay. And any bachelor students and etc.
No, bachelor students are not allowed actually into
Oh,
this
I see.
institute.
Okay, sure. Okay, so let me get started here. Okay, so the talk title is Word Embedding Language Model and Deep Learning, the trend. So I'm starting with this three gentlemen picture who got the Turing Award last year for their contribution in the deep learning and neural network. So let us get started here. So why we are talking about word vector or word embedding? Because machine does not understand text. So we have to convert text into some kind of binary format or numeric format so that machine can process it. So now text could be converted into number either in a sentence or paragraph or document, or maybe the smallest unit word. Even people are still in the current trend, people are working on the subword format. So for example, painting, I can break down painting into PA, IN, and etc., and I can do some kind of numeric transformation of those kind of unit. So that's the necessity. So now, before jumping into word vectors and etc., let us have a very quick look of what happened between what to wake, because what to wake came very late into picture, that is in 2013. But NLP does exist before from 1960s. People have been working on natural language processing since long. So what people used to do before what to wake come in picture. So if we understand the history, then we can you can accept the word to fake very easily. So what I've been talking about is text need to be transformed into some kind of uh, numeric format. And if we think about text, the smallest unit we can possibly think about is word. So before going there, let us understand some kind of law of word and text, which has been discovered in late 60s. So I'll be talking about Gibbs law. Rather, I'll be talking about I will be showing you some video, and I believe this guy can make much more drama than I can. So we'll be starting off with a video. It's a long video. I will not show everything. Maybe it's a 2 minutes or 3 minutes. I will be showing you, and then we'll be continuing. Let us start with the Gibbs law.
Hey, Vsauce, Michael here. About 6% of everything you say and read and write is the is the most used word in the English language. About 1 out of every 16 words we encounter on a daily basis is the. The top 20 most common English words in order are the of and to. In is I, that it for you was with on, as have, but be they. That's a fun fact, a piece of trivia, but it's also more. You see, whether the most commonly used words are ranked across an entire language or in just one book or article, almost every time a bizarre pattern emerges. The second most used word will appear about half as often as the most used. The third, 1/3 as often. The fourth, 1/4 as often. The fifth, 1/5 as often. The sixth, 1/6 as often, and so on. all the way down. Seriously. For some reason, the amount of times a word is used is just proportional to 1 over its rank. Word frequency and ranking on a log-log graph follow a nice straight line, a power law. This phenomenon is called Zipf's law. And it doesn't only apply to English. It also applies to other languages like, well, all of them. Even ancient languages we haven't been able to translate yet. And here's the thing, we have no idea why. It's surprising that something as complex as reality should be conveyed by something as creative as language in such a predictable way. How predictable? Well, watch this. According to wordcount.org, which ranks words as found in the British National Corpus, sauce is the 5,555th most common English word. Now, here is a list of how many times every word on Wikipedia and in the entire Gutenberg corpus of tens of thousands of public domain books shows up. The most used word, the, shows up about 181 million times. Knowing these two things, we can estimate that the word sauce should appear about 30,000 times on Wikipedia and Gutenberg combined. And it pretty much does. What gives? The world is chaotic. Things are distributed in myriads of ways, not just power laws, and language is personal, intentional, idiosyncratic. What about the world and ourselves could cause such complex activities and behaviors to follow such a basic rule? We literally don't know. More than a century of research has yet to close the case. Moreover, Zipf's law doesn't just mysteriously describe word use. It's also found in city populations, solar flare intensities, protein sequences and immune receptors, the amount of traffic websites get, earthquake magnitudes, the number of times academic papers are cited, last names, the firing patterns of neural networks, ingredients used in cookbooks, the number of phone calls people receive, the diameter of moon craters, the number of people that die in wars, the popularity of opening chess moves, even the rate at which we forget. There are plenty of theories about why language is ziffy, but no firm conclusions. And this video doesn't contain a definite explanation either. Sorry, I know that's a bummer since we appear to like knowing more than mystery. But that said, we also ask more than we answer. So let's dive into Zipf's ramifications, some related patterns, some possible explanations, and the depth of the mystery itself. Zipf's law was popular.
I'm stopping it here because it's a long video. So possibly you understand what he's trying to say, how Zipf's law could be really useful. Now let us see how Zipf's law is useful and how we can use it. So the opposite of Zipf's law is being told as Hip's law. Okay, so what is that and how it is useful? So now let us see and let me ask you, some question here. Let it be interactive. So given a language, let's say language is everywhere, right? So from what we use in our mobile phone when we type something to the Google and Facebook, and language is everywhere. We can't avoid it. So when you search something in Google actually goes back to its index table. So there is a table which consists of all the words in a language and where exactly in the pages it occurs. So what do you think, any number from the audience, what would be a number for English vocabulary? Any idea? Anybody? Or anybody? So that I know that I did not lose my audience. They're still with me.
So the audience can type it in the chat box also.
Yeah, or they can speak out if.
Yeah, they can turn on the mic and speak.
Yes. So the question is very simple. So when you search in Google, Google goes back to index table. I'm quite sure you know or you don't know the index table size. But if I ask you what is the total number of vocabulary size for a language, let's say English, any number,
1 lakh.
1 lakhs, okay, 10 billion, okay, 1 lakh and 10 billion. Anything else? Okay, fine. Let me go back. So both could be right answer. Now let us see. So the Hipps law is the opposite, law or the power law, which is described by Hipp, uh, who is a statistician. He says the vocabulary growth of a language actually follows this power law. The power law says V equal to K n to the power beta. Now, typically, he shows by a lot of experiments, this K belongs to the range of 10 to 100, and this beta is the range of 0.04 to 0.06, basically square root. So what does it mean? It means you can plot, a language and vocabulary by this kind of graph. So what this graph says, let's say you have downloaded the whole Wikipedia, and you are, reading the whole Wikipedia, and you are plotting in the x-axis how many words you encounter, total number of words, and in the y-axis you are, plotting how many new words you encounter. Okay, so let's say you read 1,000 words, how many new words appear? Then you are reading the next 1,000 words, how many new word appears, and so on. So what will happen if you keep plotting this way till certain range? You will be, receiving new word, because in the first 1,000 you will be getting, let's say, 800 new word. In the next 1,000 you possibly get 600 new words, and so on and so forth. But it will come down drastically after certain range. Okay, and then that range varies language to language, and corpus to corpus, domain to domain, and many other things. Okay, so typically for English language, this graph comes to a static level after typically 30 to 40,000. Okay, now what does it mean to us? How this is helpful? Now this is really helpful for applying so many real world problems. So for example, let's say you are working for Google, and there's a law says that, or not laws, even statistics and the real numbers shows that every 18 to 24 months web is getting double in size. Now let's say you are working for Google, and you have to manage your data center. So how big the data center should be, and how many extra cloud you have to put or throw into your data center, there should be some number. And Jeeves law can help you here. So let's say you crawl 200 GB of English web pages. What should be typically your index size? So you can apply the Hipps law, and you can really understand what would be your index size table. So 200 GB of data, and if you think 200 GB of data, one word takes how much time and how much space, you can typically think your word size is 4 to 5 characters. So you can calculate how much one word will be taking. So how many total words are there? If this much total number of words are there, then what would be the unique word size, because your index table would be unique words, or total number of vocabulary in the corpus. And if you count the typically this is the range of the total vocabulary in your corpus, then you can calculate how much how much space it will be occupying, and you can throw that amount of cloud every 18 to 24 months. So this is really helpful. Although at beginning it looks very normal, but it really helps in multiple applications in the real world. So I give a pause here. Any comment, discussion, clarification I would like to give here, if you have. And let me add to this, If you look at Indian languages, which are morphosyntactically more complex than English, because we have a lot of sandhis, we have agglutination, we have, our verb form actually change with gender, number, person, and many other difficulties and complexities are there with our Indo-Aryan languages. So word forms are much bigger, much higher than English. So typically the index size would be much, much higher. But anyway, any question here? No question? So I can go ahead. Okay, so why I'm talking about this was actually the history before we jump into the word vectors and etc. People have been, analyzing and understanding the language using mathematics. But the modern science of what to fake etc does not come just like like a dream. Just people wake up something and see something, we have to do this kind of thing, and they just create it. So it has a kind of historical development pattern. So then in early 80s, people started talking about vectors. So what is how people come into vectorification of word? For example, this way. Let's say you have a very tiny corpus. Possibly you understand that the term corpus. Corpus is a collection of text. Okay. So let's say you have a big text file which has a lot of text in a sentence or whatever paragraph format, and you are processing that. Okay. So now let's say your tiny corpus consists of 3 words, and you are trying to vectorify them. So vector is nothing but, I'm quite sure you know. If you don't know, vector is nothing but a one-dimensional vector, matrix. Okay, so it has only one row and quite a few numbers. So let's say you have these 3 words in your vocabulary: kitchenware, electronics, sports. Then you are trying to vectorify them, and you are saying, okay, this word represent here 1, this word represent here 1, and this word represent here is 1. Otherwise, it's 0. So it's called one hot vector. Why? Because only one place is hot, that is 1. Otherwise, it's 0. Now people also try to with the same philosophy to vectorify the word. The document. So let's say you have this document, the elephant squeeze at the site of potatoes and etc. So you can create a vocabulary, and wherever the particular word occurs, you can say this is 1, otherwise it's 0. Now this is fine. The problem with this is, I had this slide. Okay, so now the problem with this is, if you try to calculate distance between 2 words, let's say kitchenware and electronics, you'll be always getting √2, right? Because the Euclidean distance formulation is so 1 minus 0, 0 minus 1, and 0, 0. So basically 1 square plus 1 square, but it's basically √2 will be the distance between any 2 words. So that's a big problem, because what is the meaning or what is the necessity of creating word vector is, we can do some kind of computation on top of that. We can calculate the distance, we can use it to process the text. But if always the distance between 2 words is √2, then it's not useful. And the second problem with this is very sparse, because if my vocabulary increase a lot, 10 billion and etc., one participant says, then there will be a lot of zeros, and we will be actually wasting space, and actually wasting computation. It's not useful. So what we can do in better way? Okay. So then in 1957, there was a nice paper by this James Ford, who said, you shall know the word by the company it keeps. Although it's published in 1957, but nobody gives kind of attention to this paper. Later on in mid 80s and etc., people start using it for computation. So what does it mean actually? So earlier to that, people have been working with language, and people have been looking at grammars. Okay, so synonyms, antonyms, and hypernymy and etc. But that that method, so that route actually did not work out. So people started looking at some other way, statistical way of language. So let's say I'm giving you a word, let's say car. This is given. Let's say I give you a word. I would like to hear from the participant. Let's say computer. What are the other words coming into your mind? Very quickly. PC. Anything else? Laptop. Okay. Desktop. Okay. Machine. System. Okay. Fine. So another one, CPU. Fine. Thank you. Okay. So the idea is, if you look at a big corpus, you will be getting this kind of words are actually related. They co-occur at the sentence level or paragraph level and so on. But if you go by the route of grammar, you won't get this because they are not grammatically related. They are related by cognitive means, by the word usage and by the application of language. We learn it every day. So can we capture this kind of thing using some kind of statistics? At that point, people did not know how to do it. But can we do that? If we can do that, then while vectorification, similar words, let's say, as you said, laptop and desktop should be coming very closer. That distance would be very, very minimum. So if you can represent this way, it would be really helpful. So this actually gives birth of distributional semantics in mid 80s. So people named it distributional semantics. So can I look into a bigger corpus? Can I understand how word actually co-occurring? What is the distribution of word? And can I vectorify them in some way so that their distance, similar words would be coming at a similar range. Okay. So this is the start of Mikolov's, sorry, this is the start of Mikolov's, word to vec. Mikolov does not come out of, word to vec out of nothing. People started here, and there are a lot of research on this in the 2 decades and etc. Then the word to vec actually came out. So one of the before jumping into word to vec, let me very quickly show you the milestones of distributional semantics, and then I'll jump into word to vec, and then you will be able to kind of comprehend word to vec much better. Okay. So the first thing came out by Peter Turney in late 80s is called PMI, point-wise mutual information. So Peter Turney was a researcher at Toronto. Then he retired and joined some lab and etc. So what is this? Okay, so let's say you have a collection of words which are co-occurring etc. Let's say angry bird, let's say shopping cart, or whatever. They co-occur all the time. So can I calculate their point-wise mutual information or PMI this way? So how many times they co-occur? So probability of their co-occurring x and y divided by probability of x and probability of y, and we just use a log to get a range of that. So this is called PMI. So if we apply this, for example, my fellow letters, fellow citizen, at home, on earth, and so on. So if you calculate their bigram frequency, how many times they co-occur, it's a 22 times. How many times this word and this word occur? So you can get a PMI in the range of 6.44 and so on and so forth. So the PMI represent here is, higher the PMI is, the better they are co-occurring or they are related to each other. The lower the PMI is, they are not actually related. So for example, we and you can see some minus number here. So PMI actually helped in a lot of application in information retrieval in late 80s and early 90s. Even PMI helped a lot in the first time of Google search and all those things. Okay, now then people started looking at language modeling. Now all these ways of looking into language have been going in parallel. So see, the language processing was a problem, and everybody was trying to solve the language modeling problem by their own way, either PMI or Gibbs law or Hibbs law or language modeling or grammatical way of doing things, like Felbaum, who created the WordNet and etc., who actually got inspired from Paninian grammar in India and did a lot of things. So a lot of things have been happening at that time, and people did not know which one actually worked out. So everybody was trying their own way. So let us start with language modeling. I'm quite sure you know. So what is language modeling? So language modeling is to understand the word distribution by mathematical way. Okay. In very simple language, language modeling is nothing but fill in the blanks what we did in our school days. Now if I ask you, given these two fill in the blanks, which word will be going in the first and which word will be going in the second? So what would be your answer? Love and hate. Right. Okay. So see how you know that, because and the function word here. If we are using and here, so typically the same semantic meaning of the verb like love will be going here. If we are using but, then a different semantic or different semantic orientation of the verb will be going here. So that's the rule of the language, right? And we learn it by using. So can we capture this? I can possibly jump here to save the time, but I can show you here. So I'm quite sure you are using language modeling every day when you use your smartphone and you want to type something and it predicts the next word. That is nothing but language modeling. Okay. So now the question is how fast and how accurate language modeling could be trained on. So initially it was thought of as a fill in the blank problem, but if you look at modern NLP, if you look at BERT, GPT, I'm quite sure you have heard the GPT-3 and etc. came out. Anybody heard about GPT-3 and etc. by OpenAI? If not, you can say no. No. Okay. So if you look at modern NLP, it's actually warfare going on. Okay, so language modeling again taking the pick. So if you look at pretend language model, in recent time Google created their BERT. Okay, so it's a pretend language model trained on a huge data. So then OpenAI came up with their GPT. OpenAI is a company in California, funded by Elon Musk, who recently released their pretend language model on 45 TB of data, which is huge data, and it is working on almost everything. Then Jan LeCun from New York University, they came out with ExcelNet, which is another language model with another huge data set and so on. So this is the holy grail, and this is the way of modern NLP actually progressing. Okay, so although language, whenever I start talking about language model, it looks so innocent. It has no use and etc. But if we look at language modeling and its application in the wider range of NLP, it is everywhere. I'll come back there. So it's a fun fact, or it's a piece of trivia. So using our smartphone, we type something, right? So there was a competition by Guinness Book of World Record. Given this text, how quickly somebody can type. And the competition was given with a QWERTY keyboard, not smart keyboards and etc. So the guy who got first prize, Grace Park from US, he typed all these 56.57 seconds, almost 4.66 characters per second. But if you look at the language processing, all the keyboard you are using, Flexi, SwiftKey, and etc. in your mobile phone, a normal speed is something of this range. I don't know about the Indian languages, because Indian languages are not using really smart keyboards and etc. We have been developing something, we call it Antaryami, but that's a different story. So the idea of language modeling, what I'm trying to convey here, is everywhere. And this is a video. Maybe I cannot show the full, but I'm quite sure you have seen the Google Smart Compose in your Gmail. Did anybody try Smart Compose in Gmail? Came out 2 years back. You type just one word, and it predicts a whole sequence of words. Yes, sir. Yes, sir. Okay, good. So that's language model. Okay, so let me go and jump this. I can skip this. Okay, now let us try to formulate this language modeling problem, because when word2vec came, this actually came from two root, and two root actually come together and make the wonder. So one is distributional semantics, second is actually the language model. So what is language model and how it could be useful? Okay, so language modeling is useful for various purposes. For example, spelling correction, machine translation, part of speech tagging, parsing, even handwriting recognition, information retrieval. So most of the things possibly self-explainable. If you don't understand the first one and the handwriting recognition, let me tell you this. So for example, there's a misspelling like G multiple OOT. Now it could be normalized as good or God. So, and you can understand, or machine can understand this by looking at the context. So that's language modeling. Handwriting recognition, let's say somebody mistype in I, and machine can possibly correct this as R, because that's the more contextual here. So that could be done by language modeling. And also in many various other applications of NLP, language model is everywhere. Now, what's the problem of language modeling? So let us look at mathematical. So given a sequence of words, so we are actually trying to capture the sequence of probability of a sequence of words. So probability of a sequence of words, word 1 to word n. Okay, and we are trying to get a summation over probability of word I given the whole sequence of the previously occurred word 1 to word I minus 1. Although if you look at modern NLP, people now it has gone to bidirectional. People are not saying I will be looking into the previous word only, I will also be looking at the next word. Now you might wonder, okay, how in a situation of mobile phone it can possible? It's not possible. It actually differ application to application. Okay, when you have both the context to look at, you look at both the context. So typically machine translation or document comprehension or many other applications, summarization, you can look into both the context. But if it is a context of typing like mobile phone and etc., you only have the left context, you don't have the right context. So okay, so this is the mathematical formulation. So now what we can do, so if we write down a formulation using a standard conditional probability, we have to write this way. So how many times this whole sequence occurred from word 1 to word I, so we can have a count, and divided by how many times this sequence after the this word 1 to word I minus 1 occur, we have to write this. So how we can get this count? Let's say we download the whole web, okay, one day, and it's a huge corpus obviously, but let's say we download the whole corpus of web, and we try to count how many times this occur versus this occur, and we are trying to get the probability, and we are trying to formulate our language model. Now there are a lot of problems with this. What's the problem? The problem here is, let's say we are trying to calculate the probability of this sequence. The sequence is, if water is so transparent that so I'm trying to understand what is the probability that the word will be occurring after this whole sequence. So definitely we have to count the whole sequence. If water is so transparent that divided by count of if water is so transparent that. Now the problem with this, the language is so diverse, we can use it in so many ways. This whole sequence possibly will never occur, or maybe occur for 1 or 2 times, and this sequence maybe only occur 1 time. So the probability we'll be getting is very tiny. It may not be useful. So what is the best way we can do? So basically we can simplify the assumption by using some kind of Markov assumption. So Markov assumption is being used in several other applications in the world, but here in the language, so we can assume or we can simplify the problem by saying, okay, we'll not look into the whole sequence. We can possibly look into the two previous word or three previous word, and try to simplify the problem. So if we look at the bigram, so we can say, okay, just look at the previous word. Or if you want to look at the trigram, you will say, okay, just look at the previous two words. Don't look at the whole sequence. Okay, so this is the formulation of language modeling. Now, whether what is the right number for the context, is a 2 word or 3 word or 5 words. So there are a lot of lot of theories, and there is no firm conclusion. So it depends on the corpus size of your domain and various other factors. Okay, so typically, if you look at the literature or the NLP practices, typically for English, trigram or quadgram is just fine if you have a reasonably big corpus. Just so basically, we are simplifying the language modeling this way. If we go by the bigram, we are looking at the just previous word and dividing by the occurrence of the correct word, and this is my formulation. Okay, so now uh, let us try to understand how it will work in real life. For example, you have this tiny corpus of Berkeley restaurant reviews, which has only this many sentences, only 6 sentences, and we are trying to formulate the language modeling out of this. So how it will look? So we are creating a co-occurrence matrix. This is typically the language modeling looks like. So here the co-occurrence matrix is saying how many times 1, 2 occur together. Okay. So how many time two occur after one divided by how many times one occur in the total corpus. Okay, and you are just dividing it. So you're getting some kind of probability. And you can see it's very clear here. There are a lot of zeros, which is showing that this kind of word sequence never occur. And there are a lot of high probability number like 0.66 or let's say somewhere else. I can't say anything. So this is a high number. This is 0.28 is reasonably high here. So which is saying okay, this kind of word sequence is more probable. Okay, and this is we are trying to capture the grammar or the word sequences in a way of probability. Okay, so this is called bigram probability. Now the number of rows and number of columns will be going and will be expanding based on our vocabulary size of a given language. Okay, now if you have you seen Google Ngram? Anybody? No. So let me show you this one. Google released this corpus long back. So Google Ngram says, see, Google crawl all the corpus available in the world, right? So give me, let's say, let me show you this one. I'm trying to understand how many times Donald and Trump co-occurred together, and this is a time, this is a year. Let's see, Donald Trump. See, Donald Trump occurred here. Any other word, other diagram you would like to see? Anybody from the audience? Modi. No, it has to be a bigram. Give me a bigram. I mean, 2 words. Not Modi. Narendra Modi. Trump Modi. Okay, interesting. Let's see. Trump Modi. Now, what else? Machine learning. Okay. Machine learning. See. What else? Deep learning. Okay. Maybe deep learning was there by some other meaning. I don't know. Okay, so let us give a pause here. So you can play with this. This is available online. Just search Google and Graph and so on. But that's not the point. The point is the corpus is actually available here. It was you can see where exactly it occurs. See, the ngram data is actually downloadable from Google. It's a free. Okay, so from 1 gram to 5 gram, all the data is available, and one file size, something in GBs. So you can download and you can play and you can do something on this. You can apply this in some of your applications and so on. Okay, so this is available. So you can play with this. Okay, now let us go ahead and look into this. Okay, so okay, then so I have time till 11, right, Professor Vishwanath?
Yes.
Yeah.
Yes.
I can possibly jump many of these slides. I can directly jump into what to pick, because otherwise we'll miss many things. Okay, very quickly in 5 minutes I will talk about this, and if you have any question you can ask me, and then I will directly jump into what to pick. The problem with this kind of distributional semantics is they are also high dimensional. If you remember the way I show you the bigram probability in the co-occurrence matrix, that will be growing with the size of vocabulary. There will be a lot of zeros, and that will not be useful. Then in people started applying singular value decomposition. I'm quite sure you have heard this term in some other kind of mathematical usage of in various fields, either in mechanical science or electrical and many other fields. This is actually a very useful tool for matrix factorization. So people started applying singular value decomposition, which is actually a mathematical technique. If you have a matrix of this kind and you are trying to squeeze down this matrix, and you are still trying to keep the information available in matrix. So people apply this SVD kind of thing, and let's say for a very simple illustration, if you have a matrix of this kind of uh, movie, how people are watching movies, let's say 110 representing 11 user, and 11 column is representing a particular movie. So if you have a simple this kind of Netflix matrix, you can understand, okay, these people are actually sci-fi loving, and these people are actually romance loving people. And if you're trying to do the singular value decomposition kind of thing, you can get three matrices here, which is U, sigma, and V. This is actually your significance matrix or eigenvalues, which is representing. Sorry, I'm going a little fast, I know, but I have to. So it is actually showing the importance of a particular columns here, and you can actually squeeze down your matrix and vector this way. So people applied this in various application of NLP in late 90s. So what does it mean? It means we can actually understand the Latin semantic space using singular value decomposition. So what does it mean? So if we really go by the co-occurrence, so human and user will never come very close. Why? Because they never co-occur. So they are basically complement to each other. So when human occur, user does not occur, and also system and machine will never co-occur because they're complement. So when system occur, machine does not occur. Okay. So using co-occurrence matrix, we will never be able to understand basically these two words are actually similar. So using singular value decomposition kind of technique, people were able to actually get this kind of similarity between words, which was a very good sign of things which happened in late 90s. Let me now jump and go to word perfect. Okay, so if you look at modern word perfect, which gives us is a kind of vector representation of word, and it is pre-trained, downloadable. So what does it mean exactly? So typically, similar looking words are actually coming very closer in the vector space when you look at. So cappuccino, espresso, tea, croissants, and etc. will be coming very closer. So how word to vec works and what is the mathematics behind? So let us deep dive into that. Okay, so if you go to the word2vec website developed by Google, and if you download those pretend corpus, pretend word vectors, and if you open that, you possibly see something of this sort. Okay, for a given word, so these are some numbers as a vector. So now, if you don't understand what does this all number means, it's fine because this is not human readable. So if you don't understand, it's absolutely fine. Don't get confused or nervous by looking at that. Okay, so again, so this is what we are trying to achieve when we are doing word to vec. So we are trying to understand the context given a word. Okay, and simply we are just applying the entropy formulation here, 1 minus probability of two words given this word and the previous word. Okay, so there are two ways which actually Mikolov tried. If you go back and read his PhD thesis or those papers, you will find there are two ways Mikolov tried to solve it. One is continuous bag of word, one is skip graph. So let me give you a very basic example, then you can understand. So what is continuous bag of word? You are looking at the word sequence as a continuous manner. Okay, so you are not jumping any word. But if you are trying to understand skip gram, what is skip gram? So if you look at a sentence or language, so typically noun, verb, adjective, and adverb actually holds the meaning of a language. Any other word like function word, is, to, am, and etc. are just fillers, right? So if you drop those words, still you can possibly convey the message of a sentence. So if you jump a little bit of words, so just keep one word, two words in between, you can still understand the meaning of a sentence. So that's called skip graph. So there are a lot of applications and a lot of experiment happen in NLP using skip gram, skip one, skip two, skip three, and so on, so that it can capture the word meaning and distributional semantics, which is reasonably position independent. So that was the philosophy behind the skip gram. So now let us try to understand the skip gram model here. Okay, so now we are going deeper into word to vec, and this is the first time distribution semantics, language modeling, and a bit of neural network. Although it's not a deep neural network, even people have argued how much neural network is this, and because a very simple you know architecture and so on. So we'll not go there. So let us try to understand the basic one layer, one hidden layer neural network, and how this can solve our problem for word vectorization or word to vec. Okay. Now for this toy example, let's say we have a corpus of 5 words, W1 to W5. Okay. So this is our corpus size or vocabulary size, and this is our input layer. Now we have one hidden layer, and this is called dimensionality. Why dimensionality? So if you go to word2vec website of Google, you can see there are a lot of dimensions available for pretend word vectors, 100, 300, 700, and so on. You might be confused. So what to download? What to use? Is it 100 or 300 or 700? Now let me tell you, word2vec is nothing but distributional semantics. So the idea behind different dimensions is, if you are doing a semantically simple task like document classification, okay, so then possibly lower dimension is just fine. But if you're doing semantically complex tasks like machine translation, then possibly you have to go to 700 dimension, because you will lose a lot more information in 100 dimension. Okay, so that's the philosophy behind. Even you can try out your word to fake with lot more higher dimension that might capture a lot more information, which is not possible in 700 dimension. So now our hidden layer is has only 3 levels. So now the question is why we are squeezing it up, and why 3, why not 2, why not 1, and so on. So as I give the explanation, so there is no rule. Okay, it could be 2, it could be 1 as well. So we have to squeeze the dimensionality for sure. And that's where we have been talking about, right? So dimensional reduction was a problem in distributional semantics, because we cannot use such a big dimension vector for real-time processing. So we are squeezing the dimensionality here. Now, what we are predicting? We are predicting 3 possible words given this set of words. Okay, let's say this is my word input, W3. This is my context, W1, W2, and W4 and W5, left and right, two context. This is my given word, and I'm trying to predict all 3 possible words. So what I'm doing, I'm predicting a set of words and their probability here. Since my vocabulary size is 5, so I have to predict all 5 probabilities here in the first occurrence, all 5 probabilities in the second occurrence, all 5 probability in the third occurrence. So my context size is 3 here. This is my output layer. Okay, this is a very simple setup of word to vec, how it works. Right, now let us break it down into smaller problems. So what are the smaller problems? So now you can see there are one connection coming from each node to each node. So this is input layer, this is hidden layer, this is the output layer. So from each node of layer are actually connected with another node of hidden layer. Okay, W1 to H1. So if we say the connection between W1 to H1 is W11, the connection between W1 to H2 is W12, and the connection between W1 to H3 is W13. Similarly, the connection between W2 to H1 is W21, then the connection W2 to H2 is W22, and similarly the connection between W2 to H3 is W23. So we can create a matrix of this sort which represent all the connections and their weightage from input layer to hidden layer. Similarly, given this first context, what we are trying to do, we are trying to predict the softmax here. If you don't understand softmax, it's okay. So we are trying to predict the probability distribution of the first occurrence while our vocabulary size is 5. Okay, so O11, O12, O13, O14, and O15 is nothing but the probabilities of all the 5 words in the first occurrence. Okay, so we have connection from H1 to O11, which we are naming as W-11, and then connection from H1 to O12 is nothing but W-12, and then H1 to O13 is W-13, and so on. So we can have 3 such matrices here. So now we have 1 matrix here and 3 such matrices here. So this is our setup. Now remember, like in a normal neural network, we typically have a summation and activation function here. So summation actually club up all the incoming weightage and then use some kind of non-linear function, typically very simple function like SafePoint and etc. But if you look at modern deep learning and neural network, people are using a lot more complex function. Even people are using support vector machine in this activation function nowadays, but that's a different story. But we are using, people typically use very normal nonlinear function like sigmoid, ReLU, etc. But let me remind you again, in word2vec, we are not using any activation function. Okay, so that's why people sometimes argue word2vec is not a neural network at all. It's just a simple setup which is inspired from neural network, but it's not neural network. But anyways, so we have only summation, no activation function. So this is the simple setup here. So I would give a 1-minute pause here and try to get this picture into your brain so that I can explain this much more easily in coming minutes. Any question here?
So if there are any questions from the audience, please raise your question. You can turn on the mic and ask your question, or you can type your question in the chat box also.
Hello.
Yeah, yeah.
Yeah. Sorry, I lost. You hear me till what?
Yeah, yeah. We heard you just 1 minute before, I think.
Oh,
Only few seconds you were lost, actually.
yeah, sure. So what I was saying, there is no activation function here, only summation is there. So I will give a 1 minute break here or 1 minute pause here. Any question from participants on this slide?
Sir, I have a question here.
Yeah, sure.
Now, what could be the last function here?
What is the last function? Last function in a sense, in the last layer?
Okay.
No, what is the question? What is the function here in the last layer?
Yes, sir. Basically, we have to update these weights.
Right.
For this, so what is the last function?
Okay. It's a softmax.
Okay.
Any other question, clarification, discussion, anything is fine. Remember, no question is a silly question.
I have another question. I think
Sure.
this question makes sense.
Yeah, yeah.
So, as I remember, you have mentioned this Wake is proposed in 2013.
Right.
But for this concept, a normal artificial neural network has been used.
Right.
But these ANNs are there for means before a lot of decades. The
Right.
80s also it is there. Now, what do you think might be the reason for the emergence of what they came into the picture in 2013?
Okay. So yes, absolutely. I mean, you are absolutely right. Artificial neural network is there since 1956, from the time when Minsky and etc. actually started talking about it. So at the time, people actually things failed, right? And you know the history of this, Jeffrey Hinton, who failed and who left his job from NYU and traveled to Toronto, and still working, and he got his Turing Award in his late 70s, right? So people, somehow forget about this because it was not working at that time due to computation power, due to several other factors, data availability and many other things. So then. In 2010 and etc., computational power increase, data availability increase, and people again start looking back to neural network, and somehow it started working. And so people come back, and now it's everywhere. It's working and it's useful, simply. Any other question?
Is it answering your question?
Partially.
Okay. So which part I could not? So if you just tell me.
No, no, sir. My concern is even if with a small corpus of data, since it is artificial neural network, though at that time we don't have enough computational resources,
Sorry.
but still it can be it can be done with a small corpus of data.
Yes, but what is the question here?
So, if I understand, one can use that TF-IDF or heart vector, one heart vector, like that, and one can still use the neural networks.
Yes.
So, from where the need for word to vec came into picture?
No. So
No, sir. My question is, it's about word to vec. So for word to vec, the authors have used artificial neural net,
right.
basic multi-layer perceptron they have used.
Right.
So it was there from 1980s. Now this concept word to vec came into the picture in 2013. I don't think whether my question makes sense or not, but still, people could have proposed the same word-to-word concept maybe in 90s or 80s. Maybe it's a small corpus of data. But
Right.
why the authors or researchers took that much time in NLP to propose this in 2013?
Yes. Okay. So the answer is little complex. So yes, people could have tried, but actually the whole community lost interest in neural networks after the big failures of neural networks at that time for several reasons. So
Okay.
people did not look back at neural networks at that time. So some people have been working in isolation and was not getting much more results. So then, since again computation power increased, early 2010 actually uh, Bengio come out with his language model, neural language model, which got some attention, and people slowly started getting back towards this. So people did not believe at that time neural network works. That's why people did not look back into this.
Okay. Thank you.
Sure. Any other question? No. So let us go back. So now let us look at the mathematics, which is very simple. So now we are trying to calculate the weights from input layer to hidden layer. So if you remember correctly, so these are W11, W12, W13, and we are representing this word and the vocabulary using X1, X2, X3, X4, and X5. So what we are saying simply, so the layer in the hidden layer H1 will be getting something of this sort: W11 X1, W21 X2, W31 X3, W41 X4, W51 X5. Okay. So now similar way H2 and H3 could be calculated here, and simply we can rewrite this vector as a W transpose X. So W is the matrix of this weights and transpose of this multiplied by the x1, x2, x3, and x4 and x5, which is the input layer. If you forget, just go back here. I could have used this image in my slide. I could not. So this is the way. Sorry, we can calculate the weights of hidden layer. So that is simply W transpose X. Now we are saying renaming the net O11. So if you remember here, so this is O11. So we are getting input from hidden layer 1, 2, and 3 into this O11. So we are renaming this, saying this is U11, W dash 11 into hidden layer 1, W dash 21 hidden layer 2, W dash 31 is hidden layer 3. So again, go back. So we are getting basically 3 inputs from layer H1, H2, and H3, and we are multiplying this H1 into W dash 11, this one with W dash 21, this one with W dash 31, and we are getting the net weight of O11 using this U11, U12, U13, U14, and U15. So basically, we can rewrite for any the O, O1 and J. What is J? J is the vocabulary size. Here our vocabulary size is 5. So J will be varying from 1 to 5. So basically W dash transpose H. So this is something of this sort will be our net weight for any cell in the O. I think this is understandable. Now we have this sorry setup. Now some participant asked the question, so what is the function in the last layer? Is softmax, as I said. So what we are trying to do here is we are saying ki out of O11 is typically Y11, and we are trying to calculate the softmax here, e to the power net O11 divided by the all summation of the all cells here, e to the power net O11, net O12, 13, 14, and 15. So just simply writing this using U11, because in the last slide we said net O11 is nothing but U11, U12, U13, and U15. So this is my softmax. So what we are trying to do here is we are trying to calculate the softmax, and I'm quite certain everybody understand the gradient descent. Is there anybody who do not understand gradient descent? So everybody understands gradient descent. So what we are trying to calculate here is the weight of the softmax in the last layer, which is output layer, for the each cell using softmax. So this is the formulation. Now what we need to do is we have to calculate the errors at the last layer. So the good thing and bad thing about what to make is sorry, my throat. It is actually kind of unsupervised. It's not actually unsupervised by theoretical definition, but it is unsupervised because you just give a lot of corpus and try to learn how the word actually co-occur. Because when you are training the network, you already know what is the next word. Actual next word occur in the corpus. So you know the output. So the gold standard. So you can formulate your problem very easily, and you can train your network very easily. Okay. So now what is our objective? Our objective is to minimize the error. Right? So what we will be trying to do, we'll be trying to minimize this error, which is kind of our probability function, what we are trying to learn, given a word and the context. So we will be trying to minimize this log function, which is minus log 1 to 3, because our context size is 1 to 3. And we are trying to minimize this error, which is in a form of softmax, which we just calculated in the last slide. And we can rewrite this formulation using another summation here. We can say j equal to 1 to j, and we are just rewriting this ucj. So c is the context, j is the number of cell, and u1j, and which is the first cell of the of our context window, and j is the context. So we can rewrite this formulation by simplifying this log function. So we are saying this is a log of j equal to 1 to j, uj, and ucj. And for simplicity, we can rewrite this as this. We can write this as ycj and zcj, which is our error function. Okay. Any question here? I'm actually running a little fast, I know, because I have to finish in 11. Any quick question here?
I think there is one question from Naveen Kumar.
Huh.
He wrote in the chat box, is the class label is next word in NLP.
Is class level is the next word in NLP? No, not in NLP, but in this setup, yes. In NLP is a bigger dimension. There are a lot of things you can do in NLP, but in this setup, yes, next word is the label. But label is a different, it's a wrong terminology, because label being used when you are using some kind of classification. Here we are not doing any kind of classification, right? So it's a simple network setup, and we are trying to predict the next word. Does it answer your question? Yeah. Okay, fine. Any other question here? No. Okay. Let me again go ahead. So I just rewrite the simplified error function in the form of ycj minus zcj, and I'm saying this is my error. So what we need to do, we have to simply do the gradient descent, and we have to update all the weights. If you remember, we got some error function here, and we have to do a gradient descent and backward propagation. We have to update all the weights when we are coming back. Again, we'll be going forward direction and backward direction. So we're doing this until unless we are going to some kind of optimized format or optimized solution. So this is my error function. Now I'll be doing gradient descent. So definitely I have to do partial derivatives to understand okay, how much weight I have to change. So since I have to understand how much weight I have to change, so I have to understand, so given this O11, the weight of a given cell, how much it should change based on the weight of this neuron or W-11. So basically, again, going back, so I have this number here, which is I need to change. How much I should change this based on this weight W-11, which is connected from hidden layer 1 to O11. So that I am trying to calculate. So if I try to calculate this, I can break it down into based on the UC1, which I just calculated, if you remember, and then UC1 divided by W-11, and I just formulated this in the last slide. I said this is my YCJ and ZCJ, and I can rename this as a E1 for the simplicity. And we know this is the actual weight what we have in the O11, and we are taking a partial derivative based on the W-11, and what I am saying as a H1. So I'm saying okay, so this is my new delta change I have to do in the weight of W-11, which is E1 H1. What I'm saying, so that was the error, and this is the H1. What I'm trying to calculate the partial derivative based on this particular cell and layer. I'm saying this is E1 H1, which I need to change. Okay. Any question here? No. Okay. So let us go ahead. So now I have to change it, right? In some sense. So change means basically it could be either positive or negative. That we don't know. That will be dependent on the gradient and gradient direction. So what we are saying, we are just somehow thinking we have to do a subtraction here. So the new formulation will be W-11 minus is a sigma here, which is learning rate, minus my my delta change, whatever we are trying to do in a time of in the form of partial derivative. So O11 with the partial derivative of W-11. So this is nothing but E1 H1, what we just calculated, and this learning rate could be positive and negative based on the slope and the gradient. Okay, and we can rewrite this using simply this is our E1, what we calculated earlier, YCJ minus ZCJ, and this is HI. So this is the rewritten formulation of the gradient minus what we need to update while we are doing the backward propagation for all the context window 1 to 3, and for all the layers. Question here, if you have. No. Okay. So we learn how to do it, the error calculation from the output layer to the hidden layer. So we are all set. Now we are going from the hidden layer to input layer. Okay. So another layer. So basically we are again trying to calculate the partial derivative of the error here based on the H1. That's our weights would be. So here things are getting little more complex because we are getting three context windows, and for the all pipes, right? So things are getting little more complex here. Yes. So we are trying to calculate all the pipes from O11 to O51. So we are trying to calculate the error based on UC1 and UC1 divided by H1. So H1 is nothing but what we calculated earlier from the output layer to hidden layer. What is the change? So that is nothing but this kind of two summation function from context window 1 to 3. So O11 to O31, and all the context for J1 to J5. So we are rewriting this as a YCJ minus ZCJ as we did it earlier as well, and we are calling this as a W-1J. So this is the formulation, and now we are adding the multiplication of x1 because we have to change the value of x1 as well. That is the input for the input layer. So our rewritten formulation for the error from the hidden layer to input layer is something of this sort. we have all the five context, and all the three contextual word here: ycj minus zcj, w dash 1j into x1, and then we are rewriting this because we have to update the weights. So we are saying our earlier weight was w11 minus the learning rate, and this is our older formulation here, and we are rewriting this using this function. Any question here?
Sir, I have one question.
Sure.
Sir, suppose if in the corpus I have 1,000 words,
Right.
okay, for each word, the other 999 words combinations will be predicted, or how it is taken care, sir?
Yes, exactly. So for all the other 999 words will be predicted. That was the basic setup of Nikolov, and that's why the softmax was a costlier function to calculate at that time. And that is one of the reasons people did not use neural network that time. Then, looking at this kind of problem, Mikolov actually come up with the idea of negative sampling, and then later on people come up with the hierarchical softmax and etc. But yes, this is a problem. If your vocabulary size is 30,000, at the time when Mikolov did the experiment, the vocabulary size was in the range of 30 to 50,000. So yes, softmax need to be calculated for all the rest of the words, and it's highly, computational expensive.
Okay, sir, I got it.
Any other question? Just feel free to ask me.
So how this word to vec can be used for a classification problem? Is there
Okay.
any such relation?
Yeah, sure. So yes, it is helpful for any other problem. So let's say you have a sentence. You want to classify the sentence into either positive, negative, or neutral. It's a classification problem, sentiment analysis, right?
Okay.
So now, how you would pass in the sentence representation to a classification problem? So you can take the word vector or pretend word vector for all the words in the sentence. You just accumulate all the words, just column wise in a row, and you just represent your sentence using that vector. You pass it to your classifier and you train it. Now, instead of simple summation, you can do multiple complex things, non-linear things, and etc. But the simplest way you can do this way. Any other question?
Sir, is there any way to correlate word embedding to time series problems?
Is there any way? Sorry, what is the question? Is there any way to
correlate this word embedding to time series related problems, which varies with time, data which varies with time, can we represent and use it for classification?
Right. So my answer will be a little longer here. See, time series problem, you have to understand this is a kind of cosmetic problem. Okay, time series is a good terminology, but ultimately it comes down to either regression or classification, right? So you are looking at something as a time series. You have a certain time, kind of timestamps, and you are trying to process it, right? So if you look at RNN and etc., the modern setup of deep neural networks, it's basically nothing but time series, right? So at one instance, you are giving one word input. So, but language could be seen or could not be seen as a time series. That's a debatable question, because a sentence, if you take down 3 words, does not mean anything until unless you complete the sentence. So whether you can see the sentence as a time series, that you need to see. If you can formulate your problem in time series, yes, you can. Any other question? Okay. So let me just wrap it up. So we are done with the error calculation function. So basically, we have to repeat our gradient descent until unless we reach to a certain number of optimization, right, in the error function. So what I typically used to teach in my class. So the code of word2vec is available here. Globe is actually another updates on the word2vec by Stanford, and let me show you this one. Maybe a lot of people have already seen it, but if not, then possibly it's a good way to see, to visualize word2vec. And I used to give an assignment of acro to vec using Twitter data and hash2vec using Twitter data. So see, this is word2vec in a vector space in a squeeze format. You can see a lot of words are actually co-occurring, which are actually similar meaning. So let's say I just saw cricket. If I search cricket, cricket and cricketer are coming together. Any other word coming in somebody's mind?
Sir, machine learning, deep learning.
I don't think it will be there. It's a small thing because it's a very small, tiny data. Machines and machinery and etc. coming together. Let's say if I see car, no, car is not there. Bike. So if you see bike, so a lot of things are there. Bicycle, racing, motorcycles, ride, etc. This is a very small data. So now you might ask me a question, okay, the word vectors are really high dimensional, how they are being represented in 3 dimension. That is another problem, called Disney, etc., squeezing things and so on, which I did not cover in my lecture. But this is what word2vec produce. Similar looking or similar meaning words actually coming very close by, and that is really useful for various application down the line. So let me give a pause here, and feel free to ask me any question related to word2vec and NLP here. We have 5 minutes. Audience, any question? Any discussion?
Sir, I have a question.
Yeah, sure.
When we are writing papers to top journal, what they are
Your voice is not clear, Shabir.
Sir, am I audible now?
Sir, am I audible? Sir, am I audible now?
Still not better.
Sir, I'll type my question.
Yeah. No, now you are audible. The last sentence is pretty clear.
Okay, sir. Sir, when we are writing papers to top conferences and journals,
Uh-huh.
what they are expecting is to evaluate our proposed model with different tasks, like maybe images, languages, speech. So this is what they are expecting.
Okay.
Now, in this context, I have a question.
Mhm.
Uh,
Can you please summarize?
Again, I'm losing you. Your voice is coming, clear.
can you please summarize what are the different problems in NLP, sir? Like missing translation.
There are a lot of. Okay, no. So I possibly got your question. Let me clarify this. Okay, so now let's say I did not get time to cover this. I used to cover this in a fine lecture. So let's say word to vec came out, right? So we are proposing some kind of word vectorization. So we need to evaluate this, right? How we can evaluate? So there are 2 ways: intrinsic evaluation and extrinsic evaluation. So intrinsic evaluation has some way. Extrinsic evaluation nowadays, everybody comes to a standard. So in NLP, there are 2 standard came out called glue and super glue. Okay, so if you search for that in Google, sorry for the outer noise. Uh, so there are a lot of work there. So if you're proposing some new kind of word vectorization, you have to apply that across all those NLP tasks, and you have to show your technique is really useful for all the all the levels. Okay, so there's a benchmark. So similarly, I don't think for image processing there is any benchmark available. Even people are talking about this. A lot of discussion going on. For NLP, glue and super glue are the benchmarks you have to follow. Otherwise, people won't accept you. We have 2 minutes. Any more questions? No.
So if there are no more questions, let me ask one last question, Amtava.
Sure.
See, this word to vector is taking only linear dependency. It's like doing singular value decomposition in an iterative manner or by using some numerical method, right?
Right.
Maybe the probability matrix we're going to calculate based on the context. But why people haven't gone for non-linearity? They haven't injected non-linearity before that middle layer, or that if you inject non-linearity, maybe still the dimensionality can come down, right?
Right. Okay. So the answer is longer here. So people tried out actually, not exactly non-linearity, but in the corpus level, longer dependencies have been missed out. So that's why Globe came out, which actually bridges this two gap from Stanford. So that is the longer dependency solution road. But the non-linearity might add some longer dependency, but might lose the closer dependencies. So there are some experiment, but there is not much success on this.
So, any other questions from the audience? If there are no more questions, let me thank Dr. Amitava for a wonderful lecture on word embedding. It is a very nice lecture, and it gave the fundamentals, also many illustrations. So I think that our audience enjoyed this lecture. We thank Dr. Amitava very much for sparing his time in delivering this lecture. So thank you, Dr. Amitava.
Thank you, sir. Thanks for inviting. Bye.
So now the one announcement is that you need to type your name into the chat box, and I gave you that link also where I am saving this your attendance. I'm saving your attendance in a Google Doc. That link also I gave you. You can see that whether your attendance is marked or not. So again, I am sending the link. If your name is not there, means you are absent actually. So some of you are typing your name now. That's okay. And one of the disheartening, or one of the things that is worrying me is that the number of people attending is less than 50%. Actually, we are having 118 participants, but if you see, there are less than 50 attendees are there now. So that means less than 50% are attending to this FTP. Maybe we have to be a bit serious about attendance policy. So please attend to that one, even if you don't understand fully. Just listening may give you what is happening in the field, and later on you can explore that field in order to expand your understanding. So it is better to see what is happening nowadays in the cutting edge techniques like whatever we are doing now here. Okay. So if you are having any other questions, you can ask me now before we begin the next session. And somebody is saying yesterday also I attended, but I did not type my name. Okay, so what we can do is this name maybe I can include, but now the problem is if I allow you, then somebody else also will say the same thing. Yesterday also we asked you to type into the chat box. If you are attending throughout, you should have noticed this one. But anyhow, for NMG Kumar, attendance for yesterday, we will consider to give. And you please encourage your friends who are in this one to attend to this one. I think you don't know the list of participants, right? Maybe you can share the list of participants also. Yeah, now it is break time actually. So we are going to begin after at 11:30 we are going to begin. So until then it is break. Thank you.